when we are going to begin a new area of study, and that is groundwater. Groundwater and its contamination. Right. We have a popular belief that most of our water supplies are generally derived from surface water, say ponds, rivers, and the water reservoirs that we find on the surface. On the other hand, a large part of the water for our supply actually essentially comes from groundwater. The groundwater, how this can be defined is, groundwater is groundwater is found sandwiched between two impervious layers of rock, and can be recovered by pumping. This is what we will explain this groundwater, and it is essentially below a good depth from the surface. This is from the surface. A groundwater is about for agricultural purposes, largely for agricultural purposes. More than 50% of Indian agriculture depend on groundwater. So this is 50% of this groundwater, and again about 30% to 40% of civic use is contributed by groundwater. So groundwater globally the groundwater, the displacement of groundwater source, contamination, of groundwater source, and thirdly the loss, the depletion of groundwater source are three major problems. It's a huge problems to say. It's basically it is of such a measure. You won't be surprised to know that a large part of the world and a large section of people are continuously without the supply of water, and much of essentially due to lack of groundwater sources. Groundwater sources are getting depleted all throughout the world, I mean, what is happening is, over pumping is one key reason why the groundwater sources are, damaged. The groundwater sources are damaged and displaced. You can write displacement and damage. I will explain this damage part. Displacement and damage of groundwater source. This is a worldwide phenomena, and much more is a greater phenomena in countries like India, where agriculture is more and more using groundwater, because the surface water streams are not always available, and also many of the Indian areas are not sufficient with surface water sources. So, mostly they have to depend on groundwater, and since we do not have good canalling system in our to support our agriculture, much of the water has to be drawn from groundwater, and the farmers are forced to use groundwater. And as a result of which, what is happening is, in all cases, as the increase of groundwater source has taken place, has taken place, and urbanization has taken place. So urbanization growth, then extensive use of say groundwater, extensive use of groundwater is leading, these things are leading, you can see these things are leading various other things as well. The extensive use of essentially urbanization growth, extensive use of groundwater, then say is all leading, is leading to the contamination. If one is increase in the hardness of water, as well as contamination. Okay, contamination as well as contamination. Say contamination here, is all these cases where I have been explaining contamination. Contamination would mean the increase in criteria pollutants. Criteria pollutants are, this word criteria pollutants is known as the identified pollutants. Or identified and tracked pollutants. Identified and tracked pollutants. What does it mean? Identified is, there are many pollutants, which are, say, there are, in some cases there may be a causes of concern may be less, but in a contamination, when we are talking about contamination, the concern is high. I mean, in the sense that the water, maybe there may not be significant growth in the water about TSS and TDS, but there may be a certain increase in a concentration of certain compound or chemicals that is beyond the threshold. Let me explain you a little bit about this. You see, it does not matter, I mean, if you are studying environmental science, you should also know this. It does not essentially matter, if unclassified TDS in water increases from, say, 5,000 milligrams per liter to, say, 7,000 or 8,000 milligrams, or even say 10,000 milligrams per liter. it essentially does not cause a large chain of disturbance or effect on the population, either animals, humans, or whosoever. But it makes a tremendous sense, it is a tremendous case if you just think about a water having say 0.001 milligram per liter of arsenic, and the arsenic value getting increased by say 0.01. From 0.001, if it goes to 0.01, it is of huge concern. So when we are talking of criteria pollutants, we are only discussing about those pollutants which are critical for our information, the pollutants which need to be identified and which need to be tracked. That means how their concentration and all other things are changing have to be identified, and not only identified, they have to be regularly monitored and checked. That is what is meaning about tracking, right? So this is the contamination would mean the increase in criteria pollutants, identified and tracked pollutants in the body of groundwater. In the body of groundwater. So it's essentially groundwater is having a serious consequence, and mostly there are a larger is, as we have said in one case that I have said, it is generally said that the future wars should be fought on water, not on, in many cases, not on the petroleum or any other gases, because the way it is being depleted throughout the world is of major concern. But all this thing is as I have said is basically much depends on the urbanization, the style, the people's standard of living, how the people are living off, and all these things all taken together, I mean, is basically leading the great depletion of groundwater and as well as contamination of groundwater. Okay, let me now briefly explain about what is this the mostly, and as a result of which this aquifers, if we just see this the groundwater source. Next title is groundwater source and characterization. Groundwater source and characterization. Groundwater source and characterization. Right? What are the sources of groundwater and how do we characterize them? The characterizing means what are the typical parameters or properties that will be important for us to know to identify and characterize a particular groundwater from the another. How one groundwater would be considered different from the another is the characterization. When we are talking about characterization, we would like to know about the physical and also chemical features required of a groundwater regime. So required of a groundwater regime. The groundwaters, where they are stored, the groundwater where they are stored inside the ground is known as the aquifers. I think you have known of this aquifers as you have some idea about this aquifers. And how does it look? See here, if you just observe a groundwater source, and what we see is the soil to if we are just considering about the layers of the ground, it is like this. So this is just a section of the groundwater, section, right? We are just dealing with a section, it's both say somewhat infinite on all ends. I'll also explain this. What has happened is here, this is a soil, after this soil, we find a large unsaturated zone. Here, what is the characterization of this unsaturated zone is, this is known as the unsaturated zone. That means unsaturated zone, and this is is a basically here is this is a impervious bed, so where the water cannot go out. I mean, just for an understanding, it's not necessary that the groundwater cannot exist below this level also. Groundwater can very well exist, but then again, when it is existing, it must exist between two impervious layers, supposedly impervious layers. Now here this is the groundwater zone. If you just see this is the unsaturated. What happens is, try to understand this. This is in case of a rain. In case of a rain, the water essentially, through these pores, through different micropores, it would try to go from different sources like this, and it would carry on. This is micropores and different fissures and things like that, and mostly it would come and collect into the impervious bed. This is what is a combination of here a porous structure. Remember this is not water only, this is all groundwater sources. You will find a porous structure of rock, soil, and rock and soil both. Porous structure, where this water would essentially come and reside. The water would come and reside. This is what is from where the water is coming and going to be collected. Here, if under normal circumstances, what is happening is, so as you can see this particularly during rainy season, try to understand this. During rainy season, this level can rise. Okay, this level can rise. So during rainy season, you will find that the porous structure in which the water would be locked in would rise, right? And at the same time, when this during after the rainy season, when the summer season sets, say about this time, this level would generally go down. This level would generally go down because there will be no recharging. There will be no recharging, and very likely all these groundwater bodies are essentially continuous in nature. So here all you can see is a groundwater source being connected with another groundwater source, and that is how it is continuing. In no case a groundwater can be a single definite, definite source of water. In the sense, what I want to mean here is that they are always continuous in nature. So one groundwater linking with the another, that groundwater source is getting linked with another. So you find an infinite chain or streams of groundwater all converging and then moving away, and being connected throughout a structural manner. So the groundwater here regime in Kharagpur, regime of Kharagpur would be largely connected with the groundwater regime of Purulia, would be connected with largely the groundwater regime of Dhanbad or say Bihar areas, but they are connected, but not necessarily completely sharing the water. They are connected by all means. So what we see is a groundwater is essentially sources of water, a number of sources of water connected with each other in a continuous fashion. So A groundwater is, even if I make a drawing of a small groundwater source, remember this is just only a section of the groundwater. We are not talking about we are just mainly in all cases the groundwaters are in all cases is a continuous stream connected from one to another. Okay. Now here this is the porous structure. In this porous structure here, now let me go into another drawing here. I mean, this is of the groundwater source here. You see if you just observe this, the one we have said, this is there would be a certain bit of soil water, that is soil water, and this one is this, as I have said, unsaturated zone, mostly this unsaturated zone, this unsaturated zone, the unsaturated zone. What is happening here is, is of interest is, if you just, what do you mean by soil being unsaturated? That means, the soil will have water less than its capacity. The capacity, when the soil becomes saturated during rainy season, when you find after a great shower, you find the water being collected on top of the soil for quite some time. At that point of time, the soil is saturated. The saturated be with water, so it cannot no longer hold the water. So it would just keep the water on top of it, or it would allow it to pass through. Okay. So that is where you can find water getting collected during rainy season. So this is what is this water. Nonetheless, in a soil structure, you will get to know more. This in the soil structure, this is mostly in under all cases, when if you just observe after the rain, after some time the water goes away. Even if you do not have a connection, if you just keep the water just like that, arrange for the water at some places, without the water being flown, the water would generally go away from that place, or it would be again the old condition that it return to. So here, that is what is that when it returns to its old condition, at that point also it retains some moisture and water as well. Essentially, in a soil we can have, say, at about this time we will have about 1 to 2% of soil moisture, unless that is why you require watering during these seasons for the plants to grow, isn't it? So this is the soil water remains. This one is an unsaturated zone. There is identify this is conceptually this is the saturated zone. Conceptually, it is said that there is a zone between, what is the difference? How this is there any line delineating unsaturated zone and saturated zone? There is no. In fact, this one is basically run by a capillary zone. It's called the capillary zone. Where the water from the saturated zone would continuously move in a capillary towards the unsaturated zone. So in case this one will have due to capillary pressure, the water will move generally upwards from the saturated zone towards the unsaturated zone. So this is what it says. This particularly this zone, this saturated complete this zone is known as one typical term we generally call is there is a Vadose zone. The Vadose zone, and this one is the groundwater. This is the groundwater. groundwater regime. The groundwater regime here in this Vadose zone is completely unsaturated. So, is completely unsaturated. This is the Vadose zone. These are basically the rock formations. Certainly a permeable or pervious rock formation. Where this is the rock generally is pervious. So, allows the water to grow in, and here in most cases you will find most cases ideally it should be an igneous formation having little porosity. Igneous formation having.
So, as some surface water is going inside and in the aquifer, and we are drinking water directly from aquifer.
Yes.
So there may be chance that that is harmful.
Okay, I'll explain you that. I'll just explain you. I'll having in igneous formation having a little permeability. It is not precise or prudent enough to say that the rock is completely impervious. Rock is never completely impervious. In under all circumstances, all natural substances that we see, mostly they are pervious, but the permeability may be very low. So that is what we would talk about. So here in situation like this, we will find that this is how the groundwater essentially remains in this area. So there are few areas of importance: unsaturated zone, saturated zone, capillary zone, Vadose zone, and groundwater regime. These are the 5 things which you should have an understanding of, right. Having said this, you would go into a having said this, we will say the groundwater formation and structure. Groundwater formation and structure. To make this, to see this, we will just have a drawing. Here you see this. This is what is generally a surface topography. Say this is a surface topography, and inside this surface topography, we just have a groundwater source which is locked in an these are two impervious layers of rock. And here this is the another impervious layer of rock. Now you see this, here. Yeah, if you can just expand it to further, expand it little further here. Okay. What is happening here is this. At this point of time, say at this point, just let us say this is what is known as the unconfined aquifer. We will call this as unconfined aquifer. There is no confinement. Actually, the water is freely, water can move freely. Water can move freely. Wherever the water getting connected, they are getting moved freely. So it's called unconfined aquifer. Unconfined aquifer, right? And this is a confined aquifer. Let me explain the difference here. Why you would have a very practical significance of confined and unconfined aquifer. Here, what is happening here is like this. If you see this at this point of just at this about, say, think about 2 points here. This one is here, and okay. See, this is open to atmosphere, so it is atmospheric pressure. Okay. Here also the same atmospheric pressure is essentially applying atmospheric pressure. Okay. There would be a certain atmospheric pressure. We would just say, we would know is that, by say about H1 equivalent, H1 equivalent of the hydraulic head. You say there is a pressure of the rock which can be considered as H1 equivalent of hydraulic head. So, you just can see it is basically a mass pressure. That mass pressure is being converted into a hydraulic pressure. Okay, thinking of a water column instead of a mass, just having a water column. So here in this case, interestingly, if you just observe, so you can find, say, here this is another height that we can generally talk about. So here it is. Here, remember, it is not free and open. It's basically the rock mass working on that, and there is a pressure which can be directly transferred from the atmospheric pressure here. And if you just observe here, so you can see this is atmospheric pressure, and this one is say H3. Okay. So if you just see, if you make a difference here. So you can find out, say, in the point of difference at this point, this is the pressure that would be generated. The pressure is, if you can just, the pressure at this point. So here you can see, say, point A, say is point A, point B, okay, at this point. So here this point B. What we are seeing is, if you are just comparing the pressure here, say we are just trying to make a difference of this pressure here. So you can see there's a pressure at point B, at B, minus pressure at point A, pressure at point A. You just observe here that the difference is basically H1 plus H2, H1 plus H2 minus H3. This is this atmospheric pressure getting cancelled, isn't it? Atmospheric pressure getting cancelled. Okay, right? atmospheric pressure getting cancelled. So, in cases of whenever the situation is like this, whenever H1 plus H2 in a situation like this is more than H3, or you can find a positive value here more than 0, we can find a value more than 0. What we expect here is the water to flow from upward, and if there is a hole connecting, the water would automatically go out of this. If you can just think of a hole being connected, so this water would begin to flow out. This is what is famously known as the artesian well. Okay, I think you should not have an idea. This is an artesian well. So, in all pilgrimage site, wherever you have found that the water coming out from the groundwater is basically an artesian well in a condition of this. And you will also observe, if you just say, sometimes in many places you would see that this condition changes seasonally as well. Condition seasonally changes. So, in some cases you will find the water coming out, and some cases you would not find water not coming out. So, essentially all those situations where you have seen that water coming out, it's not by any divine help, it's merely because of this pressure condition. So, this is what is this artesian well. So, where it would require no pumping is required for the water to come out. In all other cases, to overcome the difference in pressure, to overcome the pressure to resist the pressure, to overcome and resist the pressure, one has to do some pumping. In many cases, that is wherever in other cases when in a condition like this, when H3 is more than H1 plus H2. So, in cases when this is negative or below 0, it requires pumping for the water to bring out, isn't it? So, this one is H1, H2, whenever it is less than H3, so it requires pumping. So, requires pumping in all situations, requires pumping. This is how this water basically gets out of the artesian well. This is what is particularly, this is what is there is one name to that particular level where you can get either this is the place, very likely that you can during drilling you will first strike water. This level, you see this, the topmost level here is likely to be the level where at the time of drilling you will find first strike water, in the sense that first strike water not in the form of moisture, but in the form of water dispersed into the rock structure, On top of that also there will be water, but the water will be mostly moisture, right? Water will be found in the form of vapor. But here only on this thing is, this is what is famously known as piezometric level. This is what is famously known as the piezometric level. And as well there are, in some structure, there are some structures, you will find that, in many cases, in a village also, in a village area, you will find that in some cases, even if the village is generally dry on all other areas, but there are some places there is water. In a well, people generally talk of whenever all well gets dry, but that well does not get dry. What is that reason basically? Is in many cases, if they are not special type of groundwater, what it essentially is this an aquitard, which is a local. This is called a parched aquifer, right? Parched aquifer. This would be called a parched aquifer. parched aquifer. Parched aquifer. This should be known as the parched aquifer. This one is where the water is collected in a impervious structure, in an impervious structure within a pervious structure, where water getting pervious otherwise, but there is an impervious structure, say some kind of igneous intrusion. The intrusion, the nature of the igneous intrusion in a metamorphic rock or a sedimentary rock would make that particular area to be impervious. The water would not go out. So if you are drilling a well, or if you are making a well or a drill hole, in those cases you will certainly you are going to get water. This is called a parched water table. So in most cases, whenever you find that in a place like in a place where there are not many sources or recognized sources of groundwater, yet you find in some places the water is available, generally available. This is a parched water table, where the water does not get dissipated, the water does not get displaced because of the igneous nature of the rock that holds it, igneous nature of the rock that holds it, right. So this is what has to be understood. This is what has to be understood about this groundwater formation and structure. And as you can see here, what would happen, this artesian well cannot take place in an unconfined aquifer. Remember this. At any point of time, an artificial unconfined aquifer cannot give rise to a artesian well. It has to be a confined aquifer. Only when the water is under a pressurized condition by normal means, by in a natural setting, only then the artesian well is possible. Otherwise, we find an unconfined aquifer. Unconfined aquifer, whatever water we may have, that water cannot be derived without pumping. Okay? So that makes a difference between a confined aquifer and unconfined aquifer. So it is here in a confined aquifer we generally obtain that a certain kind of pressurized condition of water, which generally allows it to come out whenever required, or things like that. I think it's clear, right. So here from in this case, this is what we would know more about as we have found out. So there would be some cases the amount of water that can be stored in a saturated aquifer, the amount of water that can be stored in a saturated aquifer, remember this, saturated aquifer depends on porosity. Depends on porosity. The porosity is known as, porosity is the volume of voids divided by the total volume. So if you are just trying to think of a structure, either rock or soil or whatever, it can be rock, it can be soil also. In such a situation, if there would be there would be the structures like this, where there will be voids, like this. So you can just see, this may be a grain of sand. These are all grain of sand. Between the grain of sand, you find some spaces always. in the rock structure also, in any kind of rock structure you will also find some voids. So, this one this is the filled portion, that is this, that is the, this, the total volume would mean, a total volume would mean, here if you just observe it like this, if you just consider it to be in a volume, this would be how it is. So, at least you make one drawing, because I will not go into this again. So, here if you can just observe this, this is what is the structure. You can see in a 3 dimension that how the structure would be. Okay. Between these structures, between these two structures, there would be always some porous, there will be some pores. These are known as the pores. These are known as the pores, or say the voids. These are known as the voids. You have learned that, I think, just for your case, just to refresh your memory here, that you can see here, this is what is this is the pores, this is the total, this is the solid portion, this is the solid. This is the solid portion. So, the total volume of the voids, divided by the total volume, or it can be total volume minus volume of the solids divided by total volume. This is voids plus solids. Total volume is the volume of voids plus solids. Okay. So, this is what is the porosity. This is one thing, one character that is important for all these aquifer. Generally this is other characteristics of the the characteristics of aquifer, how aquifer, the characteristics of aquifer is length, breadth, area and volume. I mean, measured some kind of idea about this length, breadth, area and volume. So, this is one characteristic. Then volume of water, volume of water. Yes, right. Volume of water. Then we have volume of water. We have, say, here in such cases, the length, breadth, area and volume of the aquifer, total structure of the structure.
From surface.
We generally do not say it from say depth is another important thing, depth. You can write depth, that suffices. So, says volume of water. As I have said, this porosity is one important thing.
Nature of surrounding rocks.
Nature of surrounding rocks, yes, I think in the nature of surrounding rocks, one very important thing, nature of surrounding rocks is permeability. Permeability is one important thing. Permeability, then is permeability constant or hydraulic constant. We'll say this hydraulic gradient. Then say permeability constant, as we have said, hydraulic gradient. All these things, there are a few more. There may be few more which would be important for the characteristics of the groundwater, and has to be maintained, has to be recorded properly. So, we will take up this again in the next class. We will continue with this groundwater for quite some time, and till that time I think we come to the end of the class today, and the next class I will still continue with this groundwater contamination, right. Okay. Thank you. Okay, we will start today's lecture with this, with the continuation of what we began in the last class, what we started in the last class. We are actually discussing about groundwater contamination, and there in fact, I have discussed about the characteristics of groundwater sources, the characteristics of groundwater sources, or that we known as aquifer, that we know as aquifers. Having said that, I have also discussed about porosity, and I have explained you, the porosity would mean that the total, say that the void volume divided by the total volume, isn't it? So, this would, if you just try to understand little bit about this, there are another important thing is related to porosity is this effective yield. The concept of effective yield is like this. I mean, you say, even if in many cases, if you see, it's like, suppose you have weighted your clothes, how so well you rinse it, I mean, you just turn it and all that, there would be a certain quantity of water that would be essentially coming out. Not all the water can come out, isn't it? So, that when it cannot come out, so it takes about the specific yield. Even if the water content may be say 20% or 30% of the volume, but only the available water that can be drained out would be about 20% or so. So, you find a specific yield. That is about a structure depending on a particular kind of structure. That is what is, in addition to porosity, we will also have another parameter which is known as effective yield. The effective yield suggests the water available for transportation, considering the 3 points and the distance from the equipotential line, the perpendicular distance from that point to the equipotential line, and divided by the distance. Okay. So, let me take you another example in this case. Generally, what we generally try to do is like this. Say there is an example like this. We have a plot in cases when the plots are quite in a perpendicular fashion, it is much more easier. It is much more easier to find out the equipotential line, mostly in a generally done in a grid pattern. So, you can always find out the values like this. Say here for the same case, for here this one is say 32, this one is 31, this one is 31, this one is 31, and this one is 30. Okay. There are two ways to do the procedure. One is, you can extrapolate this, to so almost the same distance at the 30th. So, this is 32. And then you can connect this to, this is becomes the equipotential line here, and then from here you can find out the perpendicular and can find out the hydraulic gradient, isn't it? So, you can find out here say A, B, C, D, E, it is F. So you can find out is hydraulic gradient is 32, 30 minus 32 minus 30 divided by AF meter cube per day on the time rate coefficient, because in many cases the speed is very slow in aquifer, so we generally need not have to represent it in terms of minute or in terms of second, things like that. Mostly if you are representing in terms of days, fair enough, because the velocity is very low. Velocity is very low, so you can see here this is known as the Darcy's law. But this Darcy's law provides to be somewhat quite simplistic in the sense that there are few things it generally understands here. If you are just observing this flow, right here, you can see this. If this is the direction, you just see if you can see in terms of the change in the hydraulic head, if you just consider this change in the hydraulic head here and the change here, you see this one is del H, this one is del L, isn't it? So this is the 2 points in the aquifer. This is the 2 points in the aquifer. This is del H, this is del L. Okay, is that clear? So having said this particularly is one flow direction. It's not necessary that the flow would be only in this direction. There would be a flow in the normal to this direction of flow as well. Normal, the spread of dispersion would be in the case of normal to the direction of this flow. So here you can see this is known as the transverse flow. This is known as the longitudinal flow.